which they should be. Yeah, we're able to see your screen. Yeah. Hi, everyone. Thanks for joining us for the NLP seminar this week. And today we have Dr. Mohit Iyer. He will be talking about a very exciting challenge in NLP that's evaluating our natural language generation systems. And if you have any questions during the talk, please feel free to post them in the Q&A chat or in the event chat, and we'll take the questions at the end. Thank you for joining us. And Mohit, I hand it over to you.
Sure. Yeah, thanks for having me. So today I'll be talking broadly about several different challenges in natural language generation, evaluation, and task design. Basically, I wanted to focus on two case studies of different NLG tasks, style transfer being one at the sentence level, and then long-form question answering, where a model has to, spit out like a paragraph-length answer being a second task. But before I get into that, I wanted to briefly kind of introduce some of the challenges in evaluation, which I'm sure are familiar to many of you, but using an example task that my group works on quite a bit. So that's story generation. And this is one of those tasks that is possibly on the difficult end of the spectrum if you look at NLG tasks like translation or summarization, where there are these well-established automatic methods that, you can argue how insightful the results from like half a point BLEU score improvement actually is, but at least it is shown to correlate to some sort of human judgments. But when you get into the realm of something as subjective as here's an example from the Reddit writing prompts subreddit, where you're given just this high-level, vague prompt with like 2 sentences and asked to write an entire story that follows from it. And so, like, this is the most upvoted story in response to this prompt. You can see that it does a lot of things, like it introduces the setting, it introduces a character, it kind of lays the seeds of some sort of interesting sci-fi backstory with the last sentence here, some new concept. And so it's doing lots of different things that we might want a model to also do, but then actually trying to evaluate these properties in generated text using either automatic metrics or human evaluation is very difficult, especially if these stories are going to be fairly lengthy. So as there was this great paper a couple years ago by Abigail C. and colleagues on just going through a bunch of automatic evaluations for story generation. And there's many interesting questions that you want to evaluate, right? Like, how related is the generated story to the prompt that you give it? How coherent is it? How syntactically complex are the stories, if you care about such things? How surprising are they? How enjoyable are they? Right? This is getting into the more subjective realm. And there's a bunch of ways you could think about to measure each one of these things, but the only reliable way to assess the overall text quality in story generation and many other kinds of more subjective NLG tasks is through human evaluation. But you can it's not trivial to set up human evaluations either, right? There's a variety of different human evaluations that people have set up in the past in story generation literature. So, for example, you can measure the relevance of generated stories by doing this first task here, where you give a shuffled collection of 3 prompts and 3 generated stories, and then you ask Mechanical Turker to match them up. And similarly, if you want to see, which story is just better, although that is incredibly subjective, you can just give workers a prompt and give them stories generated by 2 competing models and ask them to pick which one is better. But obviously, these kinds of evaluations are very high level, right? If both of your models are garbage, but one is just slightly better than the other, it's kind of meaningless to do this evaluation, right? You want an actual baseline which is strong for your results to be meaningful. And so another way that people evaluate these things are through just standard like 5 or 7 point Likert scale judgments of various properties. This is done in almost every paper on story generation, but I mean, things like enjoyability or interestingness are, again, highly subjective. You might not expect to get agreement by your workers, and they're probably not reading carefully if it's a lot of text. They might just be skimming. Um, and making the problem worse is that in the current set of NLG papers that use Mechanical Turk for these kinds of evaluations, there's a lot of important information that is not reported. So my new postdoc, Marjana, has recently been doing this survey of all NLG papers that use Mechanical Turk for evaluation, excluding translation and summarization. And there's some like really concerning signs here. Like 87% of the papers she surveyed don't report something as basic as how much you pay the worker. And this is concerning, obviously, because if you pay them less, then it's very likely that they're not going to produce high quality judgments, especially if the task is unreasonable, like, read 3 paragraphs and then give a judgment, right? If you're getting paid 2 cents per example, you're probably selecting for a set of workers that are not planning on actually doing the task. 67% of these papers don't report the qualifications that they use to restrict the subset of workers. So here, these are things like, do you select Mechanical Turkers from English-speaking countries, or what percentage of how many examples must they have completed on prior tasks before they can work on your task, or what percentage of the tasks that they've completed have been accepted or rejected, right? These are all extremely important parameters, and if you don't report them, it's really hard to take anything you say seriously. And then there's even more basic things, right? Like what is a total number of items that you had rated, or how many raters per item did you have? And surprisingly large percentage of these papers don't even report this. So it becomes a little hard to, make any useful claims from these human evaluations if they're not reproducible. And we don't even have good guidelines for, like how much should I pay on average? What hourly wage should I pay? What qualifications for a particular type of task result in the highest quality judgments? There's been similar papers recently. Dallas Card and some colleagues had a survey that was similar to this one. But this was just kind of setting the stage. There's a lot of stuff that needs to be improved in both automatic and human evaluation for NLG systems. And in this talk, I'm not really going to go into any solutions to these problems. I just wanted to give a quick plug before I begin the main part of this, which is that one thing that my group has been considering as a good alternative to the existing paradigm of crowdsourced evaluation or using these automatic metrics, which may not be very informative, is to do machine in the loop evaluation. So here you have the goal of the machine is not to produce, say, a story based on a prompt, produce an entire story, but rather it's to produce some text that will help an actual human author write their own story. So the machine is kind of like a writing assistant, and you can measure how well the machine is doing at generating text by measuring the engagement that an actual human author has with the text that the machine has generated. So for example, in this paper that we had at EMNLP, we basically use a language model as a tool to overcome like writer's block. So if you have a scene that you're about to write in your story and you have a couple of different ideas, you don't really know which one to take, this is a very common precursor to getting stuck and getting writer's block. So in these cases, we actually built or integrated our models into an existing online platform of human authors. So these authors can now click a button and they'll get some generated scene from a language model. And then they can choose to edit that in whatever way they see fit. So maybe it'll give them some ideas that they can, take on their own, or just, take bits and pieces of the generated text. Or they could just delete the whole thing and write their own thing. They have complete flexibility here, but you can measure things like how much of the text did they edit, or you can ask them survey questions. But like, these people are they are actually invested in the stories that they're writing, so you don't have to worry about things like you're paying too low, and workers are not invested in these stories. They might be too low quality to have workers on Mechanical Turk, for example, read a lot of them reliably and evaluate them reliably. So this is one alternative to consider. I'm not going to talk about this anymore, but in this talk, but you should check it out if you are interested. We have a data set and platform for people to try it out. Okay, so I'll switch over to what I am actually planning to talk about, which are these two case studies of style transfer and long-form question answering. And I'm basically going to highlight several issues with prior work for both of these tasks in evaluation and in task design, the latter mostly for the second task here. Okay, so let's jump into this. The first project I want to talk about was done by my PhD student Kalpesh and our collaborator John Weeding, who's now at Google. And it's on style transfer at the sentence level. So the task specifically, unsupervised style transfer. Let's just go ahead and break down all of the terms in all of the three things here. So style, first of all, is probably the hardest thing to define. I mean, there's no like single definition of style that is, widely accepted through many different fields of academia. There's in fact a lot of disagreement on what style is. Can it even be defined? Is it separable from meaning, etc. But we kind of take this high-level definition to be patterns of lexical and syntactic choice which are distinct from the content of a sentence. And of course, this is, a highly controversial take, this definition in sociolinguistics. But just to give a little bit more detail, so things that we're looking at are, as examples, whether a sentence is in active or passive form, how many rare words does a sentence use, what is the ratio of adjectives to nouns, how many clauses are in a sentence versus, like, is there, very long sentences being written, or are there sentences with short sentences without many clauses? Stuff like that. And Ed Hovey had this paper in 1987 that highlighted a bunch of other categories of style, like formality, simplicity, other stuff like this. So all of this is kind of encompassed in what we're trying to model here. So as I mentioned, in sociolinguistics, style and meaning are generally considered inseparable from each other. So we, in particular, are viewing style as this kind of surface form where the meaning is kind of distinct from how it's expressed. But I mean, I guess we acknowledge that style and semantics might not be separable, especially when language is used in these social contexts. But this definition, flawed as it is, might allow for real-world applications within NLP. So that's kind of what we're focused on here. And what do these real-world applications look like? I'll go over in a couple of slides. But let's get to the style transfer part now. So assuming that you are okay with our definition of style, and I have to say that even though what our definition is likely controversial, at least we tried to give one, unlike most existing style transfer papers, which just assume that style is widely accepted and self-explanatory, and there's no need to go any further. But this task of style transfer, we have an input sentence and we have some sort of target style label, and we're asked to produce an output sentence, which is essentially a paraphrase of the input, but has stylistic properties similar to the target style. And so in our formulation of this, we are trying to ensure that the semantics, the input and output are approximately preserved. So again, Ed Hovey and colleague had this paper about what is a paraphrase, right? And there were like 25 different types of paraphrases, and they define these as quasi-paraphrases. So the content is approximately the same. It might be slightly different, but there is this constraint that at least the semantics should be mostly constrained. So as an example, and you'll see why in a bit. Here's a sentence from Shakespeare: "Oh, wilt thou leave me so unsatisfied?" And if we wanted to transfer the sentence into the style of Twitter, which of course is a kind of high-level style, but we might expect to see something like this: "Oh, you will leave me so sad, question mark, sad face." The meaning is approximately preserved. I guess sad and unsatisfied, there is some difference there, but overall, like, it is approximately preserving the semantics while clearly also transferring the style. Okay. So then the unsupervised here refers to the fact that we don't have access to paired data between two styles that we cared about. So going back to this example, it would be highly bizarre to find a data set with a large number of parallel pairs from Shakespeare to Twitter, although maybe that exists. I don't know. But we assume that such data sets do not exist, and all we have are these kind of monolingual, essentially, corpora for each style. So we have all of the sentences Shakespeare wrote. We have, a huge collection of tweets. The content, of course, differs considerably from these different corpora. So, like, you, for example, wouldn't see Shakespeare writing about the NBA, right, or some TV show or whatever Young Drivers is. But you get some stylistic signal from both of these different data sets, and maybe you can do some sort of unsupervised transfer between them. Okay, so now I just wanted to highlight a major issue with a lot of recent work on style transfer, and that's that the models that people have designed significantly modify the content of the sentences. And so there's this kind of I guess, side direction that's related to style transfer called attribute transfer, where you're modifying properties such as the sentiment or the gender, whatever that means. I found that really bizarre. Or like the political ideology of a sentence or something like that. But the content is really warped. So like you can see here, these are examples from one of these papers where there's this relaxed to annoyed style transfer where you can see that the content here is completely different, right? Christmas tree and watching Star Wars becomes computer and watching The Voice. Of course, the attribute here, relaxed to annoyed, has changed. What a nice night to what a horrible way to start the weekend. But there's no kind of paraphrasing happening here, or even a quasi-paraphrase. Like the content is significantly different, right? In this one, age 18 to 24 to 65 plus, the content has completely changed. You cheated on me, but you cheated on America, but, right? There's no way, even with a very wide definition of paraphrase, you can consider these two things to be semantically similar. And I wanted to kind of go back to the original style transfer paper, which Wei and Alan wrote in 2012, I think, where paraphrasing was like, it was in the title of the paper, it was in the first sentence, right? The goal was twofold. You have to transfer the style, but you also have to produce a paraphrase of your input. And it's kind of bizarre that most of the prior work in this field just seems to have ignored the paraphrase part. And going back to the real world applications that I was talking about, all of these things, text simplification, data augmentation, etc., they all require some sort of semantic preservation. And that's just not there with many of the prior work. So this is what we're focused on, kind of bringing the paraphrase part back to style transfer. So now I'll maybe pause here if there are any questions, or if not, I can just jump ahead.
I think you can jump ahead, Mohit.
Okay, great. So I wanted to first go through our algorithm for this kind of paraphrase-based style transfer approach.
Mohit, sorry to interrupt you. There is a question from the, I just didn't see it. So this
Sure.
is among the 13% work that reported worker compensation, are there minimum wage guarantees? Have you looked at the background of these raters? There is potential crowdsourcing biases involved in the process.
Yeah, so there is a wide variance in how people report the compensation when they do, and it kind of reflects how much they've thought about this. So there are a couple papers that report that they attempted to pay a minimum wage of like $15 or $20 an hour. This is hard to estimate. Some of my previous papers have attempted to do this, and you can try and estimate the minimum wage by like how many examples can you feasibly do in an hour or something. But it's always kind of tricky when you try and apply that in practice. But most of the papers don't, and they just say like, we paid X cents per example. And there's a huge variance in what we saw. I think there was some that were as cheap as 2 cents per example, and others that were close to $2 per example. Of course, we were surveying papers across a wide range of text. So there were like sentence level tasks and also paragraph length generations that needed to be evaluated. So that could account for some of this. But really, like, there needs to be some sort of study or something at least showing the impact of compensation and qualifications on the quality of the judgments that you get. And this is what my postdoc is essentially working on now. But yeah, I mean, there's just so much variation now that it's hard to say what is reasonable and what are the impacts of paying, you know, such a low wage potentially on the quality of the judgments that you get back. Okay, yeah. So I will just move ahead then. So let's start with the model that we propose here. It's very simple. It's basically just fine-tuning to GPT-2 language models, nothing fancy there. But the interesting part is kind of how we get the data to do this. So our goal, again, is to transfer style while preserving the semantics. So let's take two of these styles, Shakespeare and Twitter. And of course, our dream would be if we had parallel data. So like if I had the sentence, Kyrie the GOAT PG, hashtag NBA from Twitter, I would really like to have the same sentence in another style, like a parallel sentence. So, you know, it could be like Kyrie Irving is the greatest point guard in the NBA of all time or something, right? Which doesn't have these stylistic signatures from Twitter. And then I could easily train, you know, some standard machine translation like model to go from the sentence that does not have the Twitter style into this sentence that we have. Unfortunately, of course, we don't have the thing on the left, right? We don't have these parallel paraphrases in different styles. So that makes our problem a little hard. And the way we tackle this is we just try and automatically create this paired data, and then we use it to train our paraphrase models. And the key insight here is that we can create this pseudo-parallel data by using what we call a diverse paraphraser. So the diverse paraphraser has a couple of properties. We want it to obviously preserve the meaning approximately of the input sentence, but we also want it to kind of warp the stylistic signature of the input to make it, for example, if we pass the Shakespeare sentence into a diverse paraphraser, we would want it to produce a sentence that does not have any attributes of the Shakespearean style. Um, so here's an example of the full pipeline. So assuming that we have this middle part here, which is the output of a diverse paraphraser, we can then complete our pipeline. So let's say, oh, all right, I don't want to cause no drama. This is our Twitter sentence, and we run it through a diverse paraphraser, and it produces, I'm not going to cause any trouble, which maybe is less Twitter-ish than the input. And then we train an inverse paraphrase model, which goes and tries to essentially take this input and kind of convert it back into the original Twitter sentence. So this second part of the pipeline is trying to inject the Twitter style back into the input sentence, which we created through this diverse paraphrasing process. So how do we actually train both of these components? So here, oh, wilt thou leave me so unsatisfied? We need our diverse paraphraser to produce something like, oh, you're going to leave me unsatisfied, right? Which does not have the Shakespearean style. And then we can train another model to put it back in. But where do we get this middle component? Before I get to that, I just want to say at inference time, the way we do style transfer from Shakespeare to Twitter is that we keep the first two parts of this pipeline the same. So I take my Shakespearean sentence, I pass it through the diverse paraphraser, I get this intermediate form, which kind of has less of the original style in it. And then I feed it to the inverse paraphraser that's trained on Twitter. So at test time, I'm basically swapping out this inverse paraphrase model, and hopefully it produces something that's a paraphrase of this intermediate sentence, but has the Twitter style. So, right, the main question is, how do we get this? How do we train the diverse paraphrase model? And we do this by using a heavily filtered back-translated data set. So some of you might be familiar with this para-NMT corpus from Weeding and Gimple 2018. It contains 50 million paraphrase pairs about by back-translating the Czech side of this incredibly large Czech-English parallel corpus. So as an example, the man is standing in the water at the base of a waterfall. You translate that to Czech, you get this, which I'm not going to try and pronounce. And then you translate that back to English to get the man at the base of the waterfall is standing in the water. So here you can see that there were some reorderings, and like this clause at the base of the waterfall is inserted into the middle of the sentence rather than at the end here. So if you look at this data as a whole, you can see that on average, the input sentence and the output sentence differ, and they differ in interesting ways. Like there's a lot of syntactic rearrangement or lexical substitutions that are interesting. And if we filter this data set to select things that we actually want our diverse paraphraser to look like, then we can actually implement this whole pipeline that I've been discussing. So the way we do this, again, is we just fine-tune GPT-2 on this parallel data that we extract from this para-NMT corpus. But we don't use the whole 50 million pair data set. Instead, we do heavy filtering. So we go from 50 million pairs down to about 75,000 pairs. And our filters, we use broadly 3 of them. So one, we filter for semantic similarity. So obviously we don't want, there is a lot of noise in this data set, and we want to remove pairs that are not paraphrases. So we filter out pairs with low semantic similarity. And then for the ones that are remaining, we further filter them based on lexical diversity. So we remove pairs that have more than 50% unigram or trigram overlap. So this is to get rid of sentences that have almost the same words in them, because we want our diverse paraphraser to be doing a lot of lexical substitution to get rid of the stylistic signature from the input. We also want to accomplish the same thing for the syntactic form of the sentence. So we remove pairs that essentially use the same ordering of the words that they shared. So you can kind of view this as like the bubble sort distance of all of the words that are shared between the two sentences. So in this way, we kind of optimize for lexical and syntactic diversity, but also keep some sort of constraint that the pairs should be similar to each other in meaning. Okay, so this is how we get the training data for the diverse paraphraser, shown with this black arrow here. And then we have the training data, obviously, for the inverse paraphraser, because it's just training from the diverse paraphraser output to the back to the original sentence that we have from our corpus. So you can think about this at a high level as using the diverse paraphraser to generate some pseudo-parallel data that normalizes the style, essentially. And we'll see a picture later on that makes this more clear. But yeah, both the diverse and inverse paraphrasers are trained by fine-tuning GPT-2 large, and we have a separate inverse paraphrase model for every style that we consider. So here we have one that produces Twitter sentences, one that produces Shakespeare sentences, and then at test time, we pass the Shakespeare sentence through the diverse paraphraser and then through the Twitter inverse paraphraser to accomplish style transfer. And by using GPT-2 large, we, of course, can leverage all the benefits of a huge pre-trained language model, which are mainly in the fluency and generalization. Okay, so having described our model, I wanted to switch over to how you evaluate style transfer, because here also there are a lot of issues in how prior work was set up. So we did this survey of like 23 recent style transfer papers and looked at how they evaluate their outputs. And so there are three different aspects of this style transfer paradigm that people care to evaluate. The one is accuracy, and here this refers to whether the output sentence that was generated has properties of the target style. Then similarity, so do the input and output, are they semantically similar to each other? Are they approximately paraphrases? And finally, fluency, so is the output grammatically correct? And so these are three different metrics, and some of these papers aggregate these three metrics down to a single score, which allows you to compare systems to each other based on just a single score. So of course that's attractive, but this aggregation process is frequently done by just computing the geometric mean of all of the three individual metrics. And this is a huge mistake, which kind of corresponds to some inflated scores of existing systems, and also of kind of really dumb baselines, as I'll show here. So let's say that I wanted to do style transfer from Shakespeare to Twitter, as our running example has been. And let's say that I have a really dumb style transfer system, which doesn't actually do style transfer at all, but say 50% of the time it just copies its input and it produces the exact input as the output. So that would look something like, this, where if my input is wherefore art thou Romeo, my output is identical. And so if you look at the three different dimensions here, I would get a 0 on accuracy, right? Because this doesn't look like Twitter at all. And I might get a 1 on the similarity because these two sentences are identical, and a 1 on fluency because, they're both fluent sentences, right? There was no model that generated. So this is the copy thing, which happens half the time. And then maybe the other half of the time, I just retrieve a random sentence from the target style. So here I have this input, why uncle 'tis a shame from Shakespeare. and my output is just a random Twitter sentence, right? Okay, we'll get back ASAP. It has nothing to do with this input. But here I would get a 100% on accuracy, right? This is, I mean, maybe if you buy that this is representative of Twitter. I would get a 0 on similarity because these two sentences are nothing alike, and a 1 on fluency, possibly. So the way that prior work has done this aggregation is you aggregate each of these metrics independently, maybe just average across all the examples. So you get 50% accuracy, similarity, and 100% for fluency. Then you take the geometric mean of that to get some aggregated score of 0.6. But this is really bad, right? Because the system does not do style transfer. Neither copying nor random retrieval is actually accomplishing the task. So this baseline, despite how dumb it is actually getting a fairly high score on this aggregated metric. And there's a very simple solution for this. But before I go into that, I just wanted to say that this system, we evaluated against some of the baseline models from the past and find that it actually slightly outperforms two of the prior state-of-the-art style transfer systems on this formality transfer task. So like it gets 58% accuracy, 38% similarity, 89% fluency, and on the aggregated score, it's slightly better than these two. So this is obviously a big problem with this aggregation metric. And there's a very simple fix where instead of doing the aggregation at the example level, first you multiply each of these scores, and then you do the aggregation on the output of the multiplied score. So here, if I multiply all three of these scores, I get a final score of 0. And then if I aggregate this, it correctly says that this model is not doing style transfer, right? Which is what we want. So this is the first thing that we propose to fix this problem. And now, using this sentence level aggregation method, we can go through some results really quickly on two different data sets. So one is formality transfer, and the other is Shakespeare to modern English transfer using the data set that Wei and Alan originally introduced. So our baselines are this unsupervised NMT system, as well as this deep latent sequence model published last year. And those are the two data sets. And so if you look at the sentence level aggregation, we see like this paraphrase-based method that we propose is doing substantially better on this formality transfer data set, as well as the Shakespeare to modern English transfer. And if you look at the results, like where is most of this gain coming from, you'll see that it is from the similarity aspect of the evaluation. So this just shows that the prior work was producing sentences that had very little semantic similarity to the input sentence. And because they didn't have any sort of explicit paraphrase constraint or anything like that, whereas ours is trained on a paraphrase data set. So you can see why we're getting these improvements. Okay, and finally, I'll just quickly go through a new data set that we released to get beyond these two existing style transfer data sets of formality transfer and Shakespeare to modern style transfer. So these existing data sets have some issues, but I think the most important one is that there's only two styles in them, right? There's either formal or informal, or there's Shakespeare and modern English, but we wanted to see if our model could handle doing style transfer between many different styles. So we collected this data set, which we call the corpus of diverse styles, by just kind of like aggregating a bunch of different types of data together. So you have Shakespeare, James Joyce, English tweets, the Bible. This stuff comes from the Koha data set, so text from like various different decades. Song lyrics, etc. So it's about 15 million sentences. I don't know why this text is so small, in 11 different styles. So you can see here that like the speech transcripts from Switchboard have a lot of disfluencies and stuff. I don't know why you would want to transfer into this, but at least it's kind of interesting to see what the models do. But they have completely different content distributions and very diverse vocabularies. These were among the reasons that we chose these 11 styles. So just going back to the diverse paraphraser part of this model, I just wanted to show as some intuition of why we apply this step. So we train a classifier on this data set to, from a Roberta CLS vector, predict the style of each sentence. And so if you train this classifier and then you cluster the CLS vectors, you see that the styles, the CLS vectors kind of nicely form different style-specific clusters. So this greenish one here is poetry cluster. This purple one over here is from Switchboard, and so on. So what we want in our diverse paraphraser is, of course, to remove the style-specific signature from the input sentence. So if you look at these CLS vectors after applying the diverse paraphraser, you can see that they become very mixed, right? There's no clear clusters. Maybe this brown one of tweets is still a little coherent here, but most of them are just mixed all over the place. And so this kind of shows the distortion effect of the diverse paraphraser and why it's an effective way of kind of normalizing out the input style. Okay, so yeah, I'll maybe skip over some of this for lack of time, but I wanted to show some examples. So here, going from Twitter to Shakespeare, we can now do in our using our CDS data set. So y'all kissing before marriage turns into and you kissed before your nuptial. It also kind of works for longer sentences. So let me read one of these. Maybe he was being terrorized into making a statement by the same means as the other so-called witnesses. So this is transferring from the style of 1990 popular English text to 1810, like how language was used at that time. A terror had been employed in the same manner with the other witnesses to compel him to make a declaration. There's a lot of syntactic and lexical changes that have been made to this input sentence. Okay, and where does it fail? We identified three main error cases. One is misunderstanding infrequent words, so like importuned. The diverse paraphraser produces import for this, even though importuned means something like harassed. And so, of course, the final sentence doesn't have this original meaning. Sometimes it drops important semantic content during the diverse paraphrasing stage. So the machine itself is made of little straws of carbon. The of carbon part, of course, very important, gets dropped. And so the machine made of straw in the final output. And sometimes it just like hallucinates random things. I'm sure many of you who work on text generation have seen similar before. Ray Hubbard kind of becomes the house of the dukedom for whatever reason. So yeah, I guess that's all I wanted to say about this project. I've been running over time, so maybe I'll just spend 5 more minutes talking about the last part before taking questions. Does that sound good?
Yeah, that sounds good. Thanks.
Okay, so clearly I should have organized this talk better, but I wanted to also discuss now turning from style transfer at the sentence level to long form question answering at the paragraph level. So here there's this data set created by Angela Fan and others in 2019 called ELI5, so explain like I'm 5. And essentially it's a filtered version of this subreddit where people ask questions like, why do humans need to eat many different kinds of foods to get their vitamins, but cows only need grass to survive? And then lots of people write answers in the comments. So I think this data set takes like the most upvoted answers and creates a long form question answering data set out of this. So this task is interesting, not only because it's a paragraph or multi-paragraph level generation task, but also because it's formulated as a retrieval and generation task. So you have this additional retrieval component. So as an example, let's take this question from before. you don't just feed this question into a language model and ask it to produce an answer. Instead, you first ask the model to retrieve relevant articles, say from Wikipedia. So you might want to retrieve documents about the cow and human digestive system. And then you can generate your output answer by conditioning on both the retrieved articles as well as the input question. So this is the way the task is formulated, and it has a public leaderboard on this KILT benchmark, which was released by FAIR, which evaluates both the retrieval and generation aspect of the task. So from the retrieval task, they manually annotate a small part of the validation data set with ground truth documents from Wikipedia that support the answer. And so then you can measure like precision and recall of your retrieval system versus the manually annotated ones. And there's also this standard automatic metrics for text generation, mainly Rouge-L, longest common subsequence, which is used to evaluate the quality of the generated answer. Okay, so I'm going to completely skip over our model. It's not the main point of this project, but we build a retrieval augmented language model that's essentially like a transformer that uses something like the retrieval functionality in Realm to retrieve documents and then condition on the generated text on them in an end-to-end fashion. And this model gets the state of the art on this leaderboard in this combined aggregated measure of retrieval and generation performance. So of course we're kind of happy to see this, but when we were doing an analysis of our model, we realized that there were several weird things going on. So probably the weirdest one is that it doesn't even seem to use the retrievals. So even though it's doing pretty good at retrieving the right documents, if at test time you swap out the retrieved documents with completely random documents, the Rouge-L score, so the quality of the generated text, doesn't really change at all. And so this indicates that the generation model is not actually benefiting much from the retrieval model, which is kind of bizarre. And so then we kind of went off on this direction of can we figure out why this is happening? And some other weird result was that, so we ran a human preference evaluation. So we took the model that has generated an answer conditioned on the retrieved document versus a random document. And it turns out that humans prefer the generated output from the model conditioned on random documents as opposed to the retrieved one, which is incredibly bizarre. And just as a sanity check, we do find that humans prefer the gold answer over the retrieved document 72% of the time. So it's very clear that the retrieval is not actually impacting the quality of the generated answer. Okay, and just to summarize some of the issues with this data set and its evaluation, the first is most salient to why the retrieval isn't actually helping here. And the answer to that, or the main answer at least, is that many of the held out questions in this data set, in the validation and test set, they have exact paraphrases in the training set, or very, very close to exact paraphrases. So here we have this example: can you protect electronics from EMPs or solar flares? If so, how? This is in the validation set. And then during training, we have questions like, how does an EMP ruin electronics? How would they be fixed? Can it be protected against, et cetera? And all these other questions about EMPs. And so 81% of the validation questions, we did this manual annotation, have an exact paraphrase in the training set. And 100% of them have topically similar questions. So this kind of indicates that a model doesn't actually need to rely on retrieving external documents because it's already seen answers to most of the questions that it's asked during training. And so this is a big issue with the data set and kind of precludes developing useful retrievers on it at this time until this is fixed. Another issue, which is kind of orthogonal, is that Rouge L is not a good way to evaluate long form question answering outputs. This is probably obvious to many of you, but it's actually quite bad in this task. So we find that gold answers, so answers that are actually written by the Redditors in the data set, often get lower Rouge scores than just completely random retrieved training answers. So here's one example. So this indicates that maybe this metric isn't well suited for this problem. And so the third issue I've already described, that conditioning the generation of answers on random documents instead of retrieved ones doesn't actually impact its quality or factual correctness. Rouge L is also biased by length, so longer outputs tend to score higher on that. And finally, we tried some human evaluations, but this is a case where crowdsourced evaluation kind of breaks down completely. Annotators find it very difficult to judge long answers that have a lot of repetition and might include some technical content which they don't have the background to judge on correctness. So just passing your outputs to Mechanical Turk is not a good solution here. And maybe just to conclude with some lower and upper bounds that we ran to demonstrate the issue. So if you're looking at Rouge L here on the validation set, selecting a random training answer gives you 16.2 Rouge L. The middle here are a couple of baselines like a BART and this RAG thing, and our model is down here, which are getting anywhere from like 18 to 24 Rouge L. And an upper bound of, so in this data set, you have many different answers for one question that have been written by different Redditors. And so if you choose the best gold answer in terms of Rouge L, this is an upper bound. Written by a human, you get 26. So the range of Rouge scores from like these completely ridiculous lower bounds of random stuff, 16 to the upper stuff, the best possible thing of 26 is really small. It's just further evidence that Rouge is not a very insightful metric for this task. And just to wrap up, quality-wise, like if you look at these outputs qualitatively, we have a really long way to go in solving this task. So as an example, why are almost all boats white? This was the question, and this is the generated text. So the first sentence is maybe not too bad. Ships are painted to provide a visible visual contrast to the sea. But then it quickly devolves into many boats have an air-breathing function that makes them easier to spot, which is a good thing if you're a pirate or trying to get into some country's waters. That's debatable, at least. And finally, there's some repetition or superfluous sentences generated. There's this Reddit formatting like edit, colon, blah, 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 which, you know, it's not, the model didn't actually edit its answer or anything like that. So yeah, there are many issues, and we don't currently have a great way of evaluating these systems, I guess, are the takeaways. So with that, I will conclude, and if we have any time at the end to take questions, I'm happy to answer them.
Thank you so much for the talk, Mohit. Very interesting insights into evaluation. Found it very interesting how metrics can be easily fooled. So I'll start with, there are a couple of questions. The first question from Veshu. Any reasons choosing to do such an aggressive filtering on the para-NMT corpus? 75K pairs seem relatively small.
Yeah, so we tried experimenting with many different data set sizes, but it turns out that GPT-2 doesn't need that much data to learn a good paraphrase model. And of course, if we kind of decrease our thresholds here for the diversity filtering, we can get more data. But we found that if we did that, the diverse paraphraser turned out to not be as diverse as we wanted it. So we can kind of measure this with looking at plots like this, or the accuracy, right? How much the style classification accuracy drops after the applying the diverse paraphrasing, and we essentially found that the most aggressive filtering worked best. And I should also say that after completing this project, one of my other students went off to Google and trained a T5 model, which is like much bigger than GPT-2, on an even more aggressively filtered version of the parent MT dataset. I think he had only like 13,000 pairs, and it qualitatively was significantly better than the one we trained. So I think the amount of data isn't a huge concern when you're starting with a very strong fine-tuned model, and more important is the quality of the data.
We have another question from Lewis. The diverse paraphrase diagram looks similar to the diagrams of disentanglement in GANs. Is there something similar going on there?
I'm not very sure. I'm not super familiar with the GAN literature. But I will say that this is, of course, not trained in anything near a manner similar to what GANs are trained in, right? We have actual supervision for every stage of this model. So, yeah, I don't think I can give any more of an insightful answer to that.
Yeah, I think that's the questions we had today. Yeah. And I think we're almost there at the end of the talk. So thank you. Thank you, Mohit.
Yeah, thanks for having me.
Thanks everyone for joining us. Bye. See you for the next talk.